Except the last one.
Let's start with chapter 3 today. Okay. We'll run with chapter 2. Just write down your attendance wherever you can find space.
Are we still on the current stuff, or is that just chapter 2?
Give me just write it on a new sheet of paper.
Oh, there's no. I mean, it's already throw it on there.
Yeah, throw it on.
Are we done with the current stuff, or it continues into chapter 3?
The current?
Yeah.
The
current,
KCL? Kirchhoff's current law?
All of that, yeah. Is that chapter 3 too?
No.
Okay. So it's one and done.
It's the 25th, right?
Yes, ma'am.
All right. What we have done is we have looked at frequency domain modeling. Right. So when we started, let me write this. So this is chapter 3, and this is called time domain model.
That's what I'm saying.
So let's take a look at this example. So this is a typical strain mass band system. I'll use FB. Spring constant K, damper with damping coefficient FV, right? When we are talking about modeling, what is modeling? Input-output relationship. Of a dynamic system. Okay. Dynamic means here you have kinetic and kinematic. The first model was you already knew before coming to class or before taking this course. Differential equation model, right? So what was the differential equation model for this? It was m d square x of t over dt plus f b d x of t dt x of t is equal to f of t. So this is a differential equation model. Okay. What did you study until now? The second model was
The electrical. Wait.
what did you study, Raju? The Laplace transform of the transfer function model, right? So the transfer function model would be what? Dm is square x of s plus fb s x of s plus k x of s is equal to, right? So this is a differential equation model. This is also a time domain model. Time domain model in calculus. This is a frequency domain model. Algebra. What we're going to study as part of this chapter is time domain model as in algebra. Okay? So we take this, or we take this, and we say differential equation model is, you can say, m x double dot, just use this format, plus f b x dot of t plus k x of t is equal to let x of t be equal to z. C of t. Let's just call this z1. And x dot of t is equal to z2.
Is that if where in the lower left corner, Laplace transform, and then you have something in parentheses? Is that above that?
Hmm?
Above that to the left?
This one?
No, below that.
Part 2.
Where it says Laplace and it says
Part 2 is
Laplace transfer function.
Okay, thank you.
This is transfer function, right?
Okay,
The transfer function model.
thank
Okay.
you.
So what we're going to assume is we're going to start with, we're going to define z1 is equal to x of t, okay, and z2 is equal to x dot of t. Now what you need to understand here is, what are these x and x dot of t for the system? For example, in this case, what is x of t?
X of t is
What are the physical, what is it physically? It's displacement. What is x dot of t?
velocity.
It's the velocity. They are called the states of the system. Okay? So displacement and velocity are states, different states. So we define this accordingly. Z1 dot, what is Z1 dot? It's equal to x dot, which is equal to Z2. You agree? And Z2 dot is equal to x double dot of t, which is equal to so what I have done is, what is the order of the differential equation here? It's a second order differential equation. I have used two variables or two states. Since it's a second order differential equation, I'll use two states, Z1 and Z2, and I define them, assign them to displacement and velocity. Okay? You do that, then if you look at this, Z1 dot is equal to x dot t, right? It's just taking different derivative on either side. That is equal to Z2. X dot is Z2. Okay. Then Z2 dot is equal to x double dot, right? If you take the derivative of the second equation, which is equal to, what is x2 double dot? So just look at this. x2 double dot will be equal to, all this will go on the right hand side, fv over n minus fv over n. You following? X dot of t minus k over n, x of t plus f of t. But what is x dot of t? Z2. Okay, what is x of t? Z1. And what is f of t? Just remember. Now if I take a and b, okay. Now do you follow this?
I'll follow the measures.
Hmm?
I'll follow the measures.
Yeah, so let's do Z1 dot equal to, Z1 will be equal to the top, right? 0 into Z1. Got it? There is no Z1 term here. 1 into Z2. There is a Z2,
Wait,
right?
I'm not.
So how do you multiply these two matrices? You go row, column, right? And row, column. If you see, there is only Z1 dot only relates to Z2. Am I capturing that in this matrix?
Yes.
0 into Z1, 1 into Z2. So Z1 dot is equal to Z2 plus 0. There is no f of t term associated with that. You see it?
So the first column is
So this is same as Z1 dot is Z2 is 0 Z1 plus Z2 plus 0 f of t. Okay, or plus 0. Just you can also write it as 1.
I actually think it helps when you write that.
Z2 dot is minus k over m Z1 minus fp over m Z2 plus 1. look at this equation, and in this equation, what A and B is written here, right? This is nothing but A and B rewritten. You agree? Do you see any changes? You don't see any changes. It's exactly the same as this, A and B, right? Now what I'm trying to do is, I'm trying to write, this is a set of simultaneous equations. I'm trying to write it in the form of a matrix. Got it? So do you see it in the form of a matrix? Z1 dot is this. Okay. So this is 0, 1, 0, 1 minus K over M minus FV over M. And Z1, Z2 is just written. So when you multiply, you get exactly the same.
So form at the top. What is the model? Is this right here
This is the model. This is part of the model. Okay. Now what you're seeing here is, see, I've taken a second order differential equation and converted that to two first order differential equations. You see it? This is a second order differential which represents the same model. Right? This is two first order differential equations. Right? 1 and 2. And the right hand side is what you're trying to solve for, is completely, there is no calculus involved in this. It's all algebra.
the one you just pointed to? Those are two first order. What was the first one you pointed to?
This is first order system. This is the second first order equation.
Before we talked about this system, you had pointed to another system.
This one. So this is the differential equation model, right? So if you look at this P, if you call this P and Q, okay. P is a differential equation model, right? It's a second order differential equation, if you look at it. So what we have done is, we have converted that to two first order differential equations. Okay. Now, the other part of this model is, here what is your output? If I define output is displacement, or what you're trying to measure. Output is nothing but what you're trying to measure in a system, what you're interested to measure. If it is that, your output equation becomes simply y is equal to 1, 0, 1.
And what's
I think it becomes 2 by 2.
No, this just becomes this one. It doesn't become 2 by 2.
what is that? That one.
That's the output. So output means y here is so if I give you, I'm interested in measuring the displacement, which is the output. So displacement is x of t, right? So y is x of t, but x of t is z1. So I look at z1, I have to follow this format. There's a particular format we're trying to follow. So z1 and z2 is kept the same. I have to just populate this matrix. Okay? It's 1, 0. So if you multiply, what are you going to get? you're going to get y is equal to 1 into z1. So this is plus 1 into z1 plus 0 into z. That's what is written.
In
Where did that y equation come from? Where did that y equation come from?
One is this gives you the input-output relationship. Okay. Now, when you talk about transfer function, right? You have to, when you develop your transfer function, you develop it for output over input. Correct? So this defines what, based on what your output, how is your output defined, this equation gets set up. This is the output equation. This does not capture the output. What specific output are you trying to measure? This equation itself will not capture what output you're trying to measure. Right? So here, for example, I will have to give you the output for you to develop the transfer function. Right? If I say the output is displacement, what is your transfer function? Just think about this. Corresponding transfer function is x of t, x of s, right, divided by f of s equal to 1 over ms square plus fbs plus a. Correct? What if I told you the output was velocity? Would the transfer function remain the same?
you put x dot.
Right. So in that case,
Did we say that the force was always the input? Did we say force was always
force
the
is always the input. So this is the input. So if this is the transfer function relating velocity to input. Right? We saw that what is velocity? Velocity is x dot of t, right? So v of s would be s into x of s. So if I'm trying to measure velocity, this is my transfer function. If my output, if my interest state I'm trying to measure is velocity, this is the transfer function. If I'm trying to measure displacement, this is my transfer function. How does this change? If I was trying to measure velocity, how would this change?
Wow.
How would this change
how would
if I
it
was trying
change?
to measure velocity? If I say output is velocity, how would this equation change?
Instead of saying Z1 and Z2 would be Z1 dot and Z0.
No? Think about it. This will remain the same. So what will this change? This will be, what did he say? Austin?
That would be Z1 dot. Or
Z1 dot.
It will be
Oh yes.
0,
uh,
1.
Wait.
Right? Because Z2 is
Oh, Z2 is x dot.
velocity. Accordingly, this matrix will change. Got it?
Where's the one in there?
and now that
Yeah.
he knows the input, right?
So
Now that he knows the
Z2
input,
is equal to x.
The input is the same. Input is captured
So
here.
that's why
okay.
now Z
Okay.
is 0.
Input is always here.
Plus 1 Z2.
Output, what is the output you're trying to measure? Output is a state of the system. You understand?
Then you got Z1.
If your output, if specified, if the output is specified as displacement, this matrix would be 1, 0. If the output is specified as velocity, this system would be 0, 1. Okay? So this is called, what you're seeing here, this is very important. So I'm going to call this C, okay? This whole thing as C.
How did you come up with that? Y equals thing? Yeah.
That's what I discussed right now. So if you define what the output is, if the output is displacement, in what in what variable is displacement captured? Is it Z1, Z2 displacement?
Yeah.
What is where? Is it Z1 or Z2 displacement?
This isn't you.
Is Z1, right? If the output is Z1, so it will be 1, 0, right?
Right, but how does it relate to the previous equation, the matrix that we came up with?
This one,
Yeah, how does that?
this is a state equation. This is the output equation. If the output, you could very well say, I want to measure both the displacement and velocity. Then what is your output equation?
1,
1.
If you wanted to do displacement and velocity, it would be 1, 1.
If I want to measure both displacement and velocity as my output, so this equation by itself will not give you, does it tell you what output you are trying to measure? Just the first one. It's not trying to. See, if you're comparing transfer function tells you what your input output. It's an input-output relationship, right? You know the input. Do you know the output? If you just look at this, the top portion, there is no input-output relationship. Together, it will tell you what is the input-output relationship. Right? You're always trying to, your domain, your modeling has to be input-output. This is the input. What is the output? Y is the output. Got it?
So that equation is also based on what you want to get.
What you want to measure. So again, these are also based on what you want to get, what you're interested in, what you want to measure. Okay, so this is, you get this? Clear? Now this equation C,
And you couldn't have an input equation, could you?
huh?
You couldn't have an input equation, could you?
Input is in your hands, right? So it's, you can vary input. It's not, it's dependent on the user, or you could vary input based on what your sensors are measuring. But input, you always know what input, how you're varying your input. Output, you have to have a relationship, because output is based on, because let's say, if you have two vehicles, two aircrafts, your input could be just displacement of the joystick, right? But the output is going to vary based on what aircraft it is. So if this captures what aircraft? The aircraft dynamics. This captures the aircraft dynamics. This will change significantly for the two aircraft. This may be the same for both aircraft, but this changes. Okay? So input is known. Input is just a known quantity on this. Equation C, I'm talking about both these combined, okay? It's called state space model. this as A. And just use these fancy letters. A, B, C. This is just Z dot. This is A. This is B. This is U. And this is just remains Y. C and Z. So this state space model is generally represented as okay. For our purposes, we won't encounter this much. So let's ignore this matrix. Okay? So what you're seeing here is, I'll discuss it when we do encounter. But what you want to focus on is z dot. What is z dot? Z dot is simply n by 1
What's n by 1?
Hmm?
What's n by 1?
Alex. N is number of state variables. Okay. So what is the number of state variables here? system, the rule of thumb we'll follow is order of system is equal to number of state variables. Got it? So what is the order of the system here? It's a second order system, so the number of state variables will be 2. Alright. So we'll look at how to use, see our goal is, given such a system, right, you're developing the dynamics, or you're developing the dynamics of a, you're developing a model of the system dynamics. What do we do with that? What are we interested in? When you're developing the system model, what are you interested in? Any system model you develop, what are you interested in?
Isn't that gonna be like how the system works?
Right, so system works or system output, system response. So this gives you the system model. Now if you know an applied input, you will always be able to know how the system works. This X of S will tell you how the system works or what is system output, system response. You're always interested in how the system responds. Okay? So that is what we are trying to understand here. And for a known input, how does the system work or system respond? So we'll look at a typical, again, a spring mass damper system and an electrical system and see how we can develop these state space representations. Okay, and we'll look at what do we do with those state space representations.
What is equation C? Which one is equation C?
All of this. So whatever is in this thing is equations. So you compare this and that. All those are, so these are, you can say these are matrices. The big matrix kind of representation. When do you want your first exam?
Let me get my calendar out.
Because I don't think we discussed a date for that.
Let's see.
How many assignments are we supposed to have before the first test?
We have a couple of them.
Oh, well then we just got our first one, so it's gonna be a while. Let me see. This is the February calendar. And we're actually.
When is your midterm? You guys know when is your midterm?
Yeah.
That's right before spring break, isn't it?
It's just before the spring break, right? So we'll have to have, how about first week of February?
That's next week.
Huh?
Next week.
Second week of February.
Second week.
Yeah.
Yeah, second week.
How about Monday? Monday
How
of,
about that Wednesday?
Monday is hectic.
This, you talking about next Monday?
No, he's talking about.
7, 9.
He's talking about the 10th.
The 10th. That's what we're talking about.
The 10th is a Wednesday.
10th? You wanted 10th?
Yeah, not a Monday. I'm fine with the 12th.
We have
Either.
meetings. I don't want to miss my meeting because I stay here like the 10th of
Oh, we surely miss it.
What?
You want to do that Friday?
That's Friday. 12? No, the 10th. No,
10th.
12 is fine. 12.
Yeah.
So that Friday is fine.
12.
12th is fine?
Yes.
So you guys